So what is a tensile test? A tensile test is perhaps the most fundamental and commonly used type of mechanical test you can perform on a material. Tensile tests are performed to determine the different mechanical properties of a material, including elastic modulus, yield strength, ultimate tensile strength, ductility, and toughness. Tensile tests are simple, relatively inexpensive, and fully standardized. So, how do they work? Well, by pulling on something, it can be quickly determined how the material will react to the forces being applied in tension. As the material is being pulled, you can visibly see how the material elongates. Tensile tests are considered to be essentially the opposite of a compression test. So why do we need to use tensile testing? Tensile tests allow engineers to predict and understand how materials will behave when they encounter tension, which is vital for designing and producing safe and effective products.
Here we have our sample being screwed on by two smaller sample mounts that are applied for experiment setup.
So next the sample is screwed into the large sample holder as shown in the video. Ensure to not over tighten the sample, but make sure it's snug. Next, ensure the holes line up and insert the pin, and then insert the smaller pin on the other side to ensure it doesn't come out. Now add the large top sample holder, screw it in snugly, and now use the bottom arrow on the control panel to lower the device into the top part of the sample holder and carefully insert the pin. It may be a little bit difficult, but eventually you'll get it. Add the smaller pin to the back, tighten the top clamp, tighten the bottom clamp, and you're good to go. After the sample is installed, place the safety shield over the tensile testing apparatus to ensure no projectiles fly out.
Here we are starting the computer program and the tensile test at the same time. Here we have our sample going through the tensile testing process. It is done at a slow pace to be able to show all of the deformations occurring. Notice the necking here. It will begin to neck more and more to eventual fracture. Notice the necking more here. Fracture will begin soon. Notice they're getting scared. And here's a slowed down video of that.
After a tensile test has been performed, we get a force distance graph, and this force distance graph can be used to derive a stress strain graph. From a stress strain graph, we can determine many different mechanical properties of material, such as its Young's modulus, modulus of resilience, yield strength, ultimate tensile strength, and toughness. The initial linear section of the graph is the elastic deformation region, which is where, when a material is under load, it will return to its original state after it has been unloaded. The Young's modulus is the slope of the linear section and is a measurement of a material's stiffness. At the top of the linear section is the yield strength, or the point at which a material loses its elastic behavior and begins to plastically deform. The modulus of resilience is the area under the curve starting from 0 to the yield strength and is a measurement of a material's ability to absorb energy when it is elastically deformed. After the yield strength point is the plastic region of the curve, and a material is initially strain hardened due to the movement and creation of dislocations. This occurs until the ultimate tensile strength is reached, or the point where the maximum stress is reached. After the ultimate tensile strength, necking occurs and the cross-section of the sample begins to decrease until fracture. The area under the curve from the yield strength to the point of fracture is a measurement of a material's toughness, or its ability to absorb energy and plastically deform without fracturing. Stress strain curves typically use engineering stress and engineering strain, but true stress and true strain curves can be derived from engineering stress and engineering strain. A true stress and true strain curve is going to have the same linear section as the engineering stress and engineering strain curve, but after the elastic region, the true stress value is going to be larger than the engineering stress value because of the decrease in cross-sectional area. Ductility can also be determined by a stress strain curve, and this is generally based off of the amount of strain that a material experiences before fracture. For example, a brittle material will experience very little strain before fracture, while a ductile material will experience a larger amount of strain before fracture.
Here we're looking at a typical stress and strain curve. Engineering stress is defined as the load or the applied force divided by the change in cross-sectional area of the specimen experienced during the tensile test. Engineering strain is defined as the change in gauge length divided by the original length. Notice that engineering stress and strain only take into consideration the deformation of the specimen at the point of fracture. However, in reality, the cross-sectional area and the gauge length change continuously under a tensile load. Thus, to improve the analysis, engineering stress and strain can be converted into true stress and strain respectively. First, in order to convert from engineering stress to true stress, let us assume that the volume of the specimen remains constant during the test, even in the plastic region. Now we are ready to perform the derivation. True stress is defined as the load divided by the cross-sectional area, which decreases during the test. Now let us derive the true strain from engineering strain. True strain is defined as the integral of the differential change in length divided by the original length. The modulus of elasticity is defined as the change in stress divided by the change in strain in the elastic or the linear region of the graph. So the elastic modulus is basically the slope of the line. The modulus of resilience is defined as the integral of the stress-strain curve from the initial point to the point where the material begins to yield. Because in this region the curve is linear, the area under the curve is simply the area of this shaded triangle in the graph. The modulus of toughness is defined as the integral of the stress-strain curve from the initial point to the point of fracture. The modulus of toughness cannot be calculated using analytical methods because the curve in the plastic region can't really be modeled with a simple known equation. Numerical methods can, however, be used to make very good approximations. Ductility of a material can be calculated in two main forms. First, it can be described as a % reduction in area. And second, it can be described as a % elongation.